Hello and welcome once again to the first part of this course. I am Mrigank. In the introduction session, I gave you a brief overview, a hint of what we are going to cover in the first few lectures on analog design. So, now let me talk about the large signal and small signal characteristics of the MOSFET that we are going to use in saturation region to arrive at the MOSFET characteristics. So, looking at the square law equation, so on the x axis I have VGS, on the y axis I am plotting the ID. So, how do I obtain this plot? I can apply a DC voltage at the gate of the MOSFET, call it Vg. I can apply a drain voltage source, say Vd. I am not talking about how to apply that drain voltage or how to generate that gate voltage. Assume that you have these sources available somehow on the chip or in the test board, you are able to generate these required DC voltages Vg and Vd and connect it to the drain and the gate of the MOSFET. Source is connected to the reference point. So, source is grounded, and now I gradually sweep my gate voltage starting from the minimum value close to 0, going on increasing the gate voltage till I reach Vt. The current will be very small, it will not be 0, mind it, because we are having sub threshold operation, and there we know that there is an exponential dependency of current on the voltage. So, in this region, of course, current is very small. For practical purposes, if we are operating the device in saturation region, we can ignore the current in this region and call it that the MOSFET is off in this region, you do not have significant current flow. Once we hit Vg equal to Vt, beyond that point we observe a steep increase in current following the square law dependency, and by sweeping the Vg from minimum all the way to a large value, we can obtain this plot. Now, how does this link to the small signal parameter of the MOSFET? So, when we talk about small signal parameter, we are talking about processing very minute, very weak signals with the help of these MOSFETs, exploiting the device characteristics, exploiting these characteristics curves of the MOSFET. So, first thing is we need to have the DC operating point, desired DC operating point of these devices known. So, what does that mean? That means that on this ID Vd VGS curve, we are going to have a desired Vg, we are going to have a particular choice of VGS, call it VGS naught, corresponding to which we are going to get a particular ID naught. So, this is defining my DC bias point of the circuit. I have chosen a certain VGS naught and the ID naught, and at this point I am going to operate my MOSFET. So, this is the operating point of the MOSFET. Now, on the top of this operating point, which is determined by the DC voltage, I can apply some small signal which is input to my circuit for amplification or processing using the physical characteristics of this MOSFET. So, I can apply a signal delta V, I can increase my gate voltage by a small amount or decrease by a small amount, which is my small signal. I can call it delta V or rather delta VGS, or in terms of small signal we can just write it as small VGS. That is a small signal change that we are imposing on the top of this circuit. So, basically I am applying a small signal in series with this gate terminal and then trying to observe what is happening to the current characteristics. So, this curve tells us that if you are increasing the gate voltage by a little bit, my drain current will go up, reduce it, the drain current goes down. So, I get a commensurate delta ID on both sides, increase and decrease by delta ID, and we can denote this MOSFET as a 3-port device. So, we can treat this as a black box. So, you have these 3 terminals that are available to you, the gate, the drain and the source. We are keeping the source as the reference point, that is grounded. We are applying some signal between the gate and source, that becomes our applied signal V g. On the top of this constant V g, we are applying some small V g going up and down, and corresponding to that we expect the current in the output branch I d, we expect some small change in the current in the I d branch, that is your delta I d. So, the net current of course is going to be I d plus minus delta I d. So, when I am applying V g plus minus delta V g, I get a corresponding I d plus minus delta I d flowing into the drain current. So, by changing the voltage across the first two terminals, I am getting a change in current flowing across the third terminal, and therefore, there is a transconductance term, transconductance operation going on. Applying a small signal voltage between gate and source, we change the current flowing between the third terminal and the device. So, we can define this three port model in terms of transconductance. So, we can draw the three ports, we have the gate, we can call it, we can just use the small signal that is applied on the top of this DC. So, we can forget about the DC V capital G, we can forget about V capital D and look at only the small quantity small V g and the resulting small I d, that is resulting in our small signal operation. So, in that case we are just going to apply some small V g over here, setting the DC to 0, and we are going to look into the drain terminal. Once again, in this particular example, if I only consider the small signal, the V d is constant. So, the drain voltage is a DC, it is not having any small signal. So, from the point of view of small signal, I set it to 0. So, I say this is an AC ground, this is an AC ground, because in the corresponding circuit over here we have set the drain to a DC voltage or V d, and as a result of the applied V g, effectively the V g s, because the source terminal is also grounded, we are getting a transconductance term, we are getting a small change in the current flowing from drain to source, and we can denote this as a constant term G m times the small signal V g s. And this small change in current, which is your small I d or delta I d, can be obtained from this transfer characteristic, from this curve I d V g s curve of the MOSFET. So, if you look at this curve and say that if you are changing the V g by delta V g, what is the change in delta I d obtained? So, that can be written as V g times the slope of this curve, right. So, G m can be defined as delta I d upon delta V g, or in terms of small signal I d by small signal V g. So, what is the small change in the drain current we will obtain when we are changing the gate voltage by small amount? That is the transconductance term, and the trans comes from the point that we are applying the signal between the first two ports and we are getting a change in current through the other port. So, if you have a conductance or a resistance, you apply voltage across the two terminals of the resistance and you get change in current across the same two terminals of the device. But here we are applying a small change in voltage across the first two terminals of the device and the current through the other terminal is changing. So, there is a trans term coming into picture, and the slope of this curve at a particular DC point that we have chosen for our circuit operation defines the transconductance of our MOSFET. And therefore, the delta I d or the small signal I d can be conveniently written as G m times V g. And remember that in this condition we have taken the source as the reference point. So, it is always with respect to the source, G m V g s becomes the transconductance. Now, in order to arrive at the expression for G m and look at how it depends upon the device characteristics that we have in our hand, we can try to derive the expression and relate it to the device parameters. So, here once again looking at the saturation region characteristics, because that is what we are going to use most of the time. We can differentiate this curve at a desired DC point V g s and V d s. So, we can obtain the slope of ID VGS curve at a particular point, as we noted in the last slide, and we can write this down as 1 upon 2 mu n COX W by L 2 times VGS minus VT 1 plus lambda VDS. And now, I can manipulate this equation that I am getting in different ways to obtain a more compact equation for GM and figure out its dependency on the device parameters. So, first case, I can multiply this equation and divide by VGS minus VT square. So, I am multiply the numerator as well as denominator by VGS minus VT. Also, I can multiply and divide by 2. So, if I look at the first term, so within this blue box, the term that I am having is same as the DC bias current that we started with, that is the ID. And the second term, VGS minus VT, is called or is generally termed as the V overdrive, the overdrive voltage. You need minimum VT with respect to the source at the gate voltage to turn the MOSFET on. The excess voltage VGS minus VT is termed as the overdrive voltage, and then this we can express this expression as 2 ID upon V over drive. This is one expression for GM. Likewise, I can modify it in a different way. I can use this equation, I can separate out, I can steal the root of mu n COX W by L, take VGS minus VT inside, make it a square, and we can to some extent, if we can afford to ignore say lambda, we can suppose the channel length modulation is we can ignore lambda, then we can drop the second term over here and just use the first term, multiply and divide by root 2, and also we are left with again another square root term u n COX W by L. So, once again the term under the first square root is our ID. So, what we get over here is root 2 ID mu n COX W by L of the MOSFET. So, this is another expression of the GM which can be handy while working on designs, when figuring out what should be the GM, what should be the gain. So, this is another expression that we should have at our fingertips. So, it tells us a couple of things. It tells us that there is a dependency on ID. If you are increasing ID for a given V over drive, your GM is going to increase, or vice versa. If you are for a particular ID, if you are reducing the V over drive, the GM is going to increase. Likewise, it also tells us that for a given ID, if you are changing the W by L, increasing the W by L, the GM is going to increase. So, once again, as I suggested, that it is not good enough to just remember this formula. It is also important that we link this expression to the actual device characteristics, that how this GM change, reduction or increase is coming when I am changing my ID or V over drive. So, it is also important to keep that into mind. So, let us look at the two dependency. So, if I revisit my ID VGS curve from which we have obtained the definition of GM, so if I am at a particular VG, so call it VG naught, source is grounded. So, as we said, the slope of this curve at this particular point is going to give me the GM. The slope of this curve is the GM. So, as per this equation, if I am say increasing the W by L, so this curve is for 1 upon 2 mu n COX W by L 1 n times VG naught minus VT square. And if I choose to increase the W by L, as I said, W by L is a design parameter available to the IC designer. I can tweak my W by L, I can change it, increase or decrease it to meet certain specs of the circuit. So, how does this curve change? So, definitely if I double my W by L. So, for a particular Vg naught, my curve is going to go up, right. Vt remains same, but the curve goes up. So, at the same value of Vg naught, we are expecting that this W by L 2, which is greater than W by L 1, we are going to get a larger slope and hence a larger GM. GM 2 is greater than GM 1, which was obtained at this point. So, keeping in mind the physical characteristics of the curve becomes very important. We should know why the change in the GM is happening. Likewise, this is the dependency on W. Likewise, we can, for the same conditions, we can also see what is the dependency on the overdrive voltage and conclude that whatever expression we are obtaining is making sense. So, once again drawing the IDVDS characteristics for the particular Vt, my W by L is fixed, my ID is fixed. The second so first equation that I have for GM is ID by V over drive. So, in this case my ID level is being fixed. So, I am at a particular ID. So, my horizontal line is fixed, and then if I am reducing my V over drive, what does that mean? This is once again VGS minus VT. That means I am reducing the VGS. So, once again for a particular characteristics, if I have to obtain the same value of ID for reduced VGS, the curve will be, the point will be somewhere over here, and this will be again a part of a different ID VGS curve. So, basically we are changing the VGS. So, once again we can clearly see that GM 2 is going to be greater than GM 1, and clearly the V over drive 2 is smaller than V over drive 1, and this gives us the dependency of GM on V over drive. So, it is important that we are able to link the small signal parameters that we are arriving at with the actual characteristics of the device. Then we can better appreciate what is the dependency of gain on W, what is going to happen if I change my bias current, what is going to happen if I have certain parameters in our hand like Vt and so on. So, this is about the small signal transconductance parameters. Let us now talk about another very important small signal parameters, that is RO of the MOSFET, which is very crucial for analog design, not so much maybe for the digital part. So, once again if I talk about the saturation region operation and look at the IDVDS characteristics of the MOSFET. So, in order to obtain this curve, saturation region operation for ID versus VDS curve of the MOSFET. So, first of all the question is, what is the curve we expect when we have a MOSFET? We are fixing the gate voltage to a DC, call it capital Vg, and we are sweeping the drain voltage this time. Remember, the reference point is source voltage. So, here in all cases we are putting the source as a reference point. So, I can always write VGS VDS, in this case Vs is equal to 0, and in this case once again we are going to sweep the drain voltage starting from 0 to some maximum value dictated by the particular choice of the gate to source voltage. So, what is the curve we expect? The well known IDVDS characteristics. So, we have already seen what happens in the triode region. So, when we start with a very small VGS, we say that the MOSFET is in triode region, and in that case the equation that is governed is the linear dependency on VGS and VDS, and we will see what is the phenomena that leads to saturation. And ideally in the saturation term means that the current should saturate, it should become almost constant, and the MOSFET should behave like an ideal current source, it becomes completely constant, it does not, should not have any effect because of changing VDS once it enters into saturation region. But the actual MOSFET characteristics tells us something else. You do have a finite slope of the MOSFET, which means that we do have some finite output impedance looking into the drain. So, let us see what all this term means the small signal output impedance or the slope of this curve, the concept of channel length modulation, and the requirement of saturation region operation. So, here this is for a particular VG1. So, what I can do is I can fix this VGS to a VG1 and then sweep my drain to source voltage from minimum 0 going all the way to higher value, and at each point I can measure what is the current ID flowing through this MOSFET. That is how I obtain this curve. I can change my VG, I can go for a larger VG, VG2, and obtain another curve. For a larger VG, of course, the saturation region as well as triode region expression will tell me that for a particular VD the current is going to be higher if I am having a larger VG, and likewise for a smaller VD I can have a curve which is lower. And graphically it is known that if you are extrapolating these curves, they meet at a particular point on the x axis, negative x axis at minus V A, which can also be termed as minus 1 upon lambda, which is a constant parameter. V A as well as lambda, I am assuming is a positive constant, positive parameter of the device. And then if I am talking about a particular VDS, VDS naught, I am looking at a particular VG naught. So, I have once again fixing the DC operating point of the device, I am choosing the bias condition of the device, I am choosing a certain VG1, and on the top of that VG1 I am choosing a certain VDS naught. So, that fixes my DC operating point, it tells me that I am at a particular DC bias current ID naught. So, this is the operating point of the device, and at this operating point I can figure out what is the slope of this curve at this operating point, because that is going to tell me something about the behavior of the output port of this MOSFET. It tells me that if I am keeping my VG constant, that is I am sticking to the VG1 curve and changing the VDS little bit across the VDS naught point. So, VDS I have kept it to VDS naught and then I am changing it little bit on both sides, delta VDS, or you can call it small signal VDS on both sides, plus minus delta. So, I am increasing and decreasing VDS by some mechanism, maybe just by tuning this knob over here artificially. So, what is the corresponding change in the current that I am going to get? So, this is going to lead to delta ID, or you can call it the small signal ID. So, what is that small signal delta ID or this small ID resulting from change in this VDS to plus minus small VDS? How do I determine that? So, I can look at this curve once again, I can see for a particular VDS, the small VDS, what is the change in delta ID that I am going to get. This is the small change in ID that I expect, right. So, once again this small change in ID can be expressed as the or the slope of this curve, delta ID, and I can write it as slope of this curve times the delta VD S, right. So, all we need is to recall what is the slope at that particular DC point. If I know the slope, I know what is the small signal behavior of this device looking at the output port. So, I can say that if I have a DC condition VDS, on the top of that I am applying a small signal VDS, what is the small change in the current ID. So, that I can obtain by the slope multiplied by this delta VD gives me the delta ID. So, I can see some questions coming in, but right now we have a question regarding GM, what is the significance of GM. So, we will once we go towards the application of this device into circuits, we will be able to appreciate what is the significance of GM. So, right now we have just looked at the transconductance operation of the device, where you are applying the input signal at the gate and getting some change in the drain. So, it is the transistor operation, right. So, you are applying signal at a certain port, you are getting current change at the different port. So, that is the main transistor operation that you are interested in. So, we will look into it when we go towards the application of the devices into circuits. Now, here once again if I talk about the small signal operation. So, starting point was we chose a certain value of VDS, we chose a certain value of VG, which landed us on this circle, on this point with a fixed VDS naught and a fixed VG, S naught, and then on the top of that we are changing the VDS. So, looking at this particular simple circuit, we are fixing this VGS to VGS naught, we are fixing this VDS to VDS naught, and then on the top of that we are changing the VDS by a little bit, by small amount, a very small signal, and then noticing the small change in ID, that is the delta ID flowing through this MOSFET, and that is easily obtained through this curve. So, I can write down what is the slope of this curve. If I look at this point, the slope can be identified as the y length, the length in the y direction divided by the length in the x direction. So, length in the y direction, the height of this point is just ID naught, right. So, I can write the slope as ID naught, because this is just ID naught starting from 0, this point is ID naught, divided by the length in the x direction, which is VDS naught plus VA in the opposite direction. So, this is the slope. Approximately, in general, the VA will be much larger than VDS naught. If I am talking about 180 nanometer technology, the supply voltage that we have is 1.8 volt, VA can be 10 or 20 volt, so almost an order of magnitude higher than VDS naught. So, for 180 nanometer, I can say VA is going to be around 20 volt or higher, VDS naught at the max 1 volt of that order. So, we can conveniently ignore this VDS naught term in presence of VA, and you can just say that the slope is approximately equal to just ID naught upon VA. So, generally this is the term, this is the expression that is used for the slope, although in the graph that I have drawn, it is not very prominently clear that VDS naught is much smaller than this VA, but generally that is the case. VA can be an order of magnitude larger than this VDS naught of desired operating point. So, generally the slope can be just defined as ID naught upon VA, and that can also be written as lambda ID. So, lambda is 1 upon VA as mentioned over here. So, we are having the slope given by lambda times ID. Now, if I want to define a quantity, that is the small signal resistance seen into the drain terminal, looking into the drain terminal, what is the small signal resistance. So, what do we mean by looking into the drain terminal? So, remember once again treating this MOSFET as the 3-port device, a black box where you have only 3 terminals visible to you, the gate, the source and the drain. You are treating the source as the reference point, you grounded it. The gate voltage is fixed at a particular VGS naught, and then on the third terminal VDS, which we can treat it as the output terminal, where we are trying to test the device, that we are changing the DC voltage over here VDS naught to a small value plus minus delta VDS, what is the change in the current. So, that gives us the quantity small signal resistance. So, for any 2-port circuit, any 2-port network or a model, the reference point may be ground, you have one port available, you want to see irrespective of whatever is there in this box, you want to see what is the impedance looking into this terminal of the box. So, I am calling this drain, this is the box, and I am calling this the drain terminal which is available to me. Other ports are fixed at some point, I do not care, the gate voltage is fixed at some point, I do not care. I am just looking at the available port, the drain, and trying to see what is the impedance, what is the small change in current that I am going to get flowing into this source if I change my voltage at this node by small Vg. So, once again it is very important to distinguish this small Vg from capital Vg. So, this capital Vd Vd. So, this capital VDS is providing me the DC point, just like on this x axis we have the DC point, corresponding to that we have a DC current ID naught. And if you are talking about the drain terminal, here we are trying to change this drain voltage little bit up and down by amount Vd, and what we are trying to do is we are trying to measure the small change in current flowing into the drain terminal. So, we are only looking at the small signal. I am forgetting about the DC condition, I am forgetting about this ID naught, I am just concerned about this small ID which is flowing into the drain terminal, the small change in current. So, this change in current becomes my small signal. I forget about the DC value, the bias point. So, what is the change in current, the small ID which is going to result from changing in the drain voltage by small amount Vd. So, this Vd upon ID is going to give me the small signal output resistance. This is going to give me the small signal output resistance, and once again this can be obtained as the inverse of this slope, right. So, what we obtained from the slope was I d upon V d. So, if I have to talk about V d upon I d, it is just the slope inverse at the particular V g naught and a particular V d naught. So, once again we have to define the slope, but at a particular DC point. So, first of all we have to identify what is the DC point at which the device is operating. So, first is identify this capital V d s naught, capital V g naught, capital I d. So, that gives me the operating point, and on that operating point, at that point, what is my slope? Inverse of that slope is giving me the R o, and therefore, this becomes equal to 1 upon lambda I d or V a upon I d. So, this is the bias point voltage DC current. Now, before we try to combine these two parameters G m and R o to arrive at the combined small signal parameter of the MOSFET, let us briefly talk about the channel length modulation. Although many of you might be already aware of it, quite thorough with it, but once again people working in digital domain, they hardly worry about lambda, they hardly worry about R o. So, in those cases it is good to have a brief recap of this mechanism, underlying mechanism behind R o or the channel length modulation and the resulting slope. Let us revisit that very quickly. So, if I look at the MOSFET structure, recap of channel length modulation. So, considering the NMOS once again. So, what we have seen is that if you are having a gate voltage V g beyond a certain voltage called V t, that is the threshold voltage, we have the MOSFET getting on. So, as long as the V g is lower than the threshold voltage for V g minus V s, V s is the reference point, we are assuming it to be grounded. So, for a V g s less than V t, there is hardly any current, there is hardly any conduction. So, practical purposes we can ignore it. We do have subthreshold current, there is always bear in mind that we do have subthreshold current, but if we are operating with larger bias current, we can ignore that. So, below V g s less than V t, we do not have much conduction in the channel. So, here we have a p type substrate and a lot of holes over here, but we do not have a significant amount of electrons forming the channel. Once we go beyond V t for V g s greater than V t, we induce enough number of electrons in the channel. So, when we are increasing the gate voltage, essentially what are we doing? We are depositing more and more positive charges on the metal gate. Making a metal terminal positive means you are depositing more and more positive charge, and these positive charge will attract more and more negative charge at this point. The more is the positive charge, you will require more amount of negative charges over here to balance the electric field created by the positive charges. So, the moment you are trying to deposit positive charges on the gate terminal, trying to make it more positive, we need negative charges on the other side of this oxide to balance the electric field or terminate the electric field. So, they are these positive charges, they produce an electric field and they attract the negative charges, so that they accumulate over here and form the channel. So, that is the basic mechanism, right, for forming an N type channel. So, beyond a certain point, when your V g s is sufficiently larger than V t, you have enough number of electrons accumulated over here, so that the substrate region has become almost N type as the bulk is P type. So, if we say that if the electron concentration in the bulk, or sorry, the hole concentration in the bulk is P hole, the electron concentration at V g equal to V t, almost we can call it N electron, is equal to P hole. That is called channel inversion. That happens only when your channel is completely inverted beyond V g equal to V t. So, that is Of course, we can go to more device level operations and we can derive the exact physical phenomena involved in that. We can derive the physical meaning of VT, but in this limited session, of course, we cannot do that. We can point out to the reference material, so that those of you who are interested in going to the device details and brush up the device fundamentals can do that. The VT itself is a very important parameter. It has many important dependencies on other parameters. So, it is important that you are aware of VT also, the origin of VT also. So, I would definitely recommend getting into the basic device concepts and be aware of this concept of channel inversion, that how the p type substrate is getting inverted, how you are putting more and more positive charges on the gate, and that is attracting more and more electrons on the surface and creating an n type channel connecting the two n plus regions. So, once this happens, we say that the channel has been formed. You have enough number of negative charges accumulated over here and their density is equal to the hole density in the bulk. So, that is the channel inversion, channel has been inverted. Now, as we said, the channel inversion depends upon the relative difference of the voltage between the gate and the silicon. The gate is metal, in between you have oxide, and then you have the channel, which is once again silicon. So, metal, oxide and silicon, it is forming a capacitor. So, in order to form a channel in any section of the MOSFET, if I redraw this a little bit more detail, if I have to talk about any particular location, suppose the source is at a ground voltage and this is oxide, we are talking about the gate voltage Vg and the drain voltage is small. Suppose it is small, close to 0, it has to be positive, right, little bit positive voltage is needed to ensure any current flow. If you have both source and drain 0, there is no current flow. So, you need a potential drop to have current flow. So, assume that it is close to 0, little bit 0 plus. So, you have some current flow provided the channel is created. Now, Vg is greater than Vt. So, under that condition, as I said, we are going to have a channel of electrons created. You have deposited so many positive charges over here. To balance those, you are having a lot of negative charges over here. So, you are having the channel created. At any point in the channel, the effective density of these electrons at a particular location y, suppose I call this my reference point 0, and at a particular location y in the channel, I am looking at the electron density at this point, that is going to depend on the difference between the gate potential and the channel potential. So, there is going to depend upon the difference between the Vg at this point and the channel potential V channel at y, right. V channel means the channel potential at the y. Vg is all throughout constant, right. This is the metal gate, metal does not have significant potential drop. So, all throughout Vg is constant, right. So, this is entire region Vg, but in the channel you have a relatively higher resistance. So, you have a potential drop across the channel starting from the source going all the way to drain. So, the potential is dropping across the channel. This is a higher resistance material silicon, and therefore, V channel y is not constant. V channel is dropping from a positive potential on Vd side going down all the way to 0 at the drain side. So, V channel y is a variable. As a result, at a particular slice, if I take out the slice of the MOSFET and try to see what is the effective potential between this capacitor of metal, oxide and silicon at this point, that is going to be Vg minus V channel y, that is what we have written over here. And in order to invert the channel, V channel, this effective voltage must be greater than Vt. So, in order to have the channel at the source side, we said that Vg should be greater than Vt, because on the source side the effective potential between the gate and the channel was just Vg. This is close to 0, because this is adjacent to the source which is having 0 potential. So, at this point we just have the overall potential between the gate and channel as Vg, but at a particular location Vy, it is reduced to Vg minus V channel, and therefore, in order to have the channel continuous at the location Vy, we must have Vg minus V channel greater than Vt. Now, if you go on increasing Vd and make it more and more positive and reach a condition such that Vd has reached say Vg minus Vt. So, under that condition, just adjacent to the channel, just adjacent to the drain terminal, if I look at the V channel, at drain the Vy or V channel Y, let me V channel Y is approximately equal to Vd, which is Vg minus Vt, and therefore, effective voltage drop across MOS, that is the metal oxide in semiconductor, it is reduced to just Vt, because this is going to be Vg minus Vt. If we go beyond that, if Vd increases beyond this, then definitely the effective voltage is reduced below Vt, and once again you are going to lose the channel at that point. So, we say that under that condition the channel has been pinched off, you do not have an effective electron density on the drain side. So, at this side the channel has been pinched off, the electron density over here has been reduced to 0, but definitely on the source side you still have the strong channel created. So, this is basically now creating a depletion region, and what happens if we go on increasing the drain voltage further. So, if my Vd is going beyond Vg minus Vt, so for some point in the channel, so some y in the channel, we will have V channel y equal to Vg minus Vt. So, at some location in the channel, we will have a condition where V channel is equal to Vg minus Vt. So, if I just continue from here, so if I am going for larger and larger Vd, so we expect that at some point in the channel, definitely down there, we are going to have V channel y equal to Vg minus Vt, and once again at this point we are reaching a condition where Vg minus V channel y has been reduced to Vt. So, the pinch off point moves further. So, this entire region is depleted of electrons, you do not have enough electron in this region, we say that this is depleted, and therefore, the effective, we call this delta L, the effective channel length across which the length the channel is formed is now reduced to L minus delta L. Now, it can be shown if we try to derive this equation from the very basics. All we need to do in order to capture this effect of reducing L is to modify the channel length, the effective channel length appearing in the MOSFET to L minus delta L, because what happens is that you are having a depletion region beyond this point. So, in this region you are having a lot of positive charges. So, a lot of negative fixed charges over here in the p type region, and you have a lot of negative charges in the n plus region. So, here in this depletion region, just like in the depletion region of the diode, here we have a depletion region and we are going to have a strong electric field in this region. So, whatever electrons are able to reach till this point, they are easily sucked in. So, in order to write down the overall equations for the current, I can just modify my equations and replace the L by an effective channel length, as if my channel length has been reduced to L minus delta L, and imagine that my channel ends over here, and then whatever current I get, that same current is going to exit out of this channel. That is not going to change because current cannot change. So, my modified ID becomes 1 upon 2 mu n Cox W by L minus delta L Vgs minus Vt square. So, all I have done is the original current equation I have modified to L minus delta L, and assuming the delta L to be relatively small, here I have exaggerated it, it is looking larger, but in general if I assume that the delta L is small as compared to the channel length, I can take out L out of it and we are left with 1 minus delta L upon L Vgs minus Vt square, and this can be expressed as 1 minus x, where x is very small, assuming x is much smaller than 1. For delta L much smaller than L, I can express this equation as 1 minus mu n Cox W by L Vgs minus Vt square 1 plus delta L upon L. And once again this delta L upon L is a fractional change in the current, can be written as lambda times Vds. That is once again coming from the device characteristics proportional to Vds. If you are increasing the Vds, making the drain voltage more and more positive, the delta L increases, the pinch off point shifts further, and as a result the current is supposed to increase slightly, and the proportionality constant is once again coming from that slope of IDVDS characteristics. So, smaller is the lambda, smaller will be the change. In that case, we can ignore this delta L by L, but if the lambda is smaller, especially if you are going for scale technologies, lambda degrades, and as a result it becomes more and more significant. The slope in the saturation region becomes more and more prominent. We cannot treat it as an ideal current source. This is the basic origin behind channel length modulation. I can write down the overall current equation as Cux W by L Vgs minus Vt square 1 plus lambda Vds. So, once again remember that here we have taken certain approximations rather than deriving it from the basics and arriving at the final equation because of lack of time. We have just said that the key point to remember is your effective channel length is getting reduced. The length over which you are calculating the current flow, it is just L to L minus 0 to L minus delta L, and we are assuming that the drain is shifted to this point, because after this there is no significant electron concentration. So, whatever mechanism we use to arrive at the original current equation, we just change the limit of L to L minus delta L, and whatever current reaches here, because of the strong electric field in this region, it gets sucked in towards the drain, which is positive potential, which is Vd greater than significantly greater than Vg minus Vt. You have a positive potential over here, a strong electric field in this direction, which sucks in all electrons that reaches here. So, that is the basic mechanism. For more detailed device level derivations, we can once again provide you some extra notes. We definitely do not have so much time to go through that in this course. So, this is basically gives us the small signal operation and the characteristics that we used in our previous discussion about the channel length modulation, right. So, this characteristic that we obtain, it comes straight from this equation, or you can say this characteristics is being well captured by this equation, the lambda Vds representing the dependency of the drain current on the drain to source voltage. So, a good MOSFET, an ideal MOSFET will be such that lambda is close to 0. So, that the curve is almost flat. So, that the channel length modulation is almost negligible, delta L is much small as compared to L. That is an ideal MOSFET, because what do we need for a good transistor? The good transistor is such that the current is being controlled only by the voltage between gate and source. That is the good transistor, because we want transistor operation. The voltage across the 2 ports should control the current flowing across the 3rd port. The voltage across the 3rd port should not control the current. That is a good transistor. So, for analog operation, for good amplification, we need good RO, a very small slope, a very small channel length modulation. So, that the delta L upon L is very small. That gives us a better device suitable for analog amplification, as we will see in the continuation of this lecture. So, this is talking about the 2 small signal parameters GM and RO. We will come back and we will try to combine these 2 parameters and complete the small signal model of the MOSFET, and on the top of that we will then try to add the small signal capacitances to develop the high frequency model, visit the concept of noise, and try to add the noise sources to the MOSFET to complete the model for our circuit analysis. So, that is what we are going to do in the next class, and in the last session once again we will start with the circuits and try to apply these models for analyzing the circuits for frequency response, for AC analysis, noise analysis, small signal analysis, DC analysis, and so on. All right. So, I will definitely we will have an interaction session also towards the end, where we will try to address some of the key questions that are being posted. So, I will so there is a time for the break right now. We will meet once again after the break, maybe after an hour or so at around 1:45 p.m. Thanks a lot.